Hello, welcome to our fourth week of distance learning. For this week, we're going to explore more complicated ways of counting. So last week, we talked about permutations and combinations. So this week, we're actually going to go over um, one of the more complex methods used in counting, but these are definitely derivatives of permutations and combinations. And do remember that permutations and combinations came from the fundamental principle of counting. So definitely that is also important for this week's topic. Anyways, before we actually begin, let's go over the PGCPS online safety guidelines. Okay, here we go. So again, please be reminded that the PGCPS administrative procedures regarding appropriate use of technology, social media, and email continue to apply to our online instruction. Again, for this particular statement, it's not going to be interpreted literally as how it's phrased because this is already a pre-recording. So if you would like to actually share this video to a friend of yours who actually needs to learn more about similar topics that I'm actually going to share this week, do let me know. So you can actually send me an email, and then I can give you, of course, a written permission, and then you can, of course, let your friend view the recording. Anyways, that is just, of course, to make sure that we adhere to the safety protocols that PGCPS is trying to enforce on us. Also, do remember that if you actually want to learn more about the applicable procedures about this online or the responsible use of technology, definitely check it out on the student handbook, which can be, of course, found in the PGCPS portal. But if you'd like, you can actually just go to our Google Classroom and go scroll down all the way to the beginning of to the earliest post I actually put up, because I did put up a link to get you straight to the student handbook. Okay, now that this is out of the way, we can now proceed with our main lesson, which is about more complex methods of counting. Okay, so here we go. All right, here we are, people. More complex counting. All right, so in this particular lesson, I'm actually going to go over three particular scenarios where the counting is not as easy as the ones we've had earlier. But if you actually remember the guiding principles that were used in order to answer the questions from the last few weeks that we've been discussing, then this one should not be too difficult to follow. But before we actually go to the lesson proper or to the examples, let's go over the lesson objectives first. All right, so at the end of this lesson, students are expected to solve more complicated examples of counting problems. So this one would require use of fundamental principle of counting, permutations, and combinations. Okay, and definitely to combine different techniques in counting to solve word problems. Right, so these two objectives go hand in hand. So you are expected to solve more complex problems, and you are to use all the techniques that we have learned so far in order to answer them. Okay, so I will give you 3 examples of scenarios where the counting is more complicated than what we've usually encountered. Okay, so first we review. So permutations and combinations, right? So we did talk about them. So permutations and combinations, they have 2 requirements. Number 1, you cannot repeat what you have already selected. So if you are choosing from 10 objects, right? If you've chosen one already to be in the first, if you've already chosen one, you cannot choose the same object for your second position or for your second choice. So definitely there is no repetition of choices. And the second condition is that all the choices must be together. That means you cannot choose one and then you are free not to choose on the other. Okay, so you have to choose all the R objects, right? So permutations, P and R. So when I was looking at the Google Forms and your answers, you would denote it as writing R first before N. So take note of the proper notation. So first you write how many objects you are going to choose from, and then you need to write how many objects you would like to choose. So if you would like to choose 2 objects from 8 objects, then that could be P8, comma 2, read as P8 taken 2, or it could be C8 taken 2, right? So notice that permutations can be computed this way. And remember, the exclamation mark is, of course, the factorial symbol. Okay, so combinations are computed this way. So notice how similar the formulas for permutations and combinations are, except that combinations has an extra divisor here, R factorial. That means the number of combinations is definitely much fewer than the number of permutations that can be made. The reason is that permutations consider the arrangement. So if you choose 3 objects out of 10, it matters how they were chosen for permutations. But for combinations, as long as it's the same 3 objects chosen, it doesn't matter which was chosen first, right? So you need to be very aware about this difference. Okay, so also note that N is the number of objects that a person can choose from. So this is the total number of objects that a person is able to choose from. And R is the number of objects that a person needs to choose. So the person can choose all of them, in which case it looks more like Pn taken N or Cn taken N. Okay, that's fine. Right? Or if the person does not want to choose all of them, then of course it just reduces to R objects. Okay, for permutations, there is of course the added condition that the objects chosen must also be arranged. So the arrangement can happen while choosing. It can also happen after choosing. It doesn't matter as long as at the end of the scenario, the objects are going to be arranged. This is how permutations can be differentiated from combinations, right? So when you are deciding whether to use permutations or combinations, you ask yourself, do I need the objects to be arranged or no? If you answer in the affirmative, if you say yes, go for permutations. If you answer in the negative or you answered no, then go for combinations. So this is how you differentiate permutations from combinations. Okay, so here are some identities, right, that we can use to actually make calculations simpler. Okay, so permutations, so P, N taken N, that means you're going to choose all of them and you are going to arrange them. right? So not only do you choose all of them, you also would like to arrange them. So that is simply n factorial. Okay, so if you need to choose all n objects and arrange them, that is simply n factorial. You don't need to write p n taken n. You can just say n factorial. Right? C of n taken r is actually the same as c taken n minus r. The reason is that if you are going to choose r objects, that means you are not going to choose n minus r objects, right? So out of 5, if you need to select a pair, then there is 3 objects that you're not going to choose, right? Because you're only choosing 2 objects. So the number of ways you can choose 2 objects is the same as the number of ways as the number of ways that you choose which ones you don't want to pick, right? So if you want to pick 2 objects out of 5, that's the same number of ways you choose the 3 that you will not pick. It's reverse, right? It's like picking the ones you'll throw in the trash. Okay, so the number of ways is the same. All right. If you think about it really hard, it would make sense, right? Because it's like I'm picking for keeps, or I'm picking things that I'm going to put in the trash or I'm going to disregard. So they should have the same number of ways to choose. All right. Then finally, C, N, taken N. That means you're going to choose everything. That is simply 1, of course. There is only one way that you choose everyone if there is no particular arrangement. Now, if you are going to choose only 1, or if you're going to choose everyone except 1, then that, of course, that has several ways. That can be done in several ways. But if you are going to choose all of them, then there's only one way to do that. Just choose all of them. All right. Okay, so I hope that that is pretty clear for you guys. If you do have questions with what I have discussed, definitely do post them in the Google Docs so that I can actually address them during my office hours. All right. Sometimes I do log in when I don't have anything to do. All right, so when I'm checking the Google Forms you turned in, sometimes I do check and then sometimes I do answer. But definitely do post them there so I can actually address them when I see them. All right, so I think after this, we're going to now see the first example. Right, so let's look at it. Okay, so the first example is arranging objects that needs to be arranged next to each other. So we're going to arrange objects that need to be next to each other. All right. So this one is slightly different because usually we just either choose objects and not worry whether which ones are next to each other. But there are cases wherein you have to choose objects, you have to arrange them, and some of them need to be next to each other. Let us consider the example. So 20 books are to be arranged on top of a long cabinet. There are 5 books for English, 7 books for science, 4 books for math, and 4 books for social studies. Each book having a different title. Okay, the question is, how many ways can all the books be arranged so that books on the same subjects are next to each other? Now take note, each book has a different title. So if you consider English, it could be, let's say, English 1, then English 2, English 3, English 4, then I don't know, Advanced English maybe. Right? So those are different title books. So definitely, we can distinguish each book from each other. Now, I need to make that clarification now because the next example would actually highlight the scenario wherein some objects cannot be distinguished from one another. All right. Now, if you'd like to try this out on your own, right, you want to see how advanced your counting, your understanding of counting principles are, you may definitely pause the video now Okay, try to like list down your answer. It's not necessary that you compute the actual number, because I don't think I did. I think I just left it in terms of permutations or factorials. Okay, and then I unpause the video later, and then we can see the answer and the solution for this particular problem. Okay, right. I think that should be enough time for you guys to actually try and make a decent attempt. Of course, after pausing the video, right? And then unpausing it now so that we can actually go over the solution. Okay. Okay, so to be able to do this, of course, the next slide would feature out the solution, but I think it's prudent if I actually go over the solution with you as we are trying to solve that. Okay, so we're going to... All right. Okay, so the problem states that we have to arrange 20 books. 5 of them are for English. 7 are for science. My God, I'm having difficulty spelling science. 4 for math, and 4 for social studies. All right, so how are we going to arrange these objects if books belonging to the same subject stay with each other? All right. So the idea or the strategy in answering this one is to actually group each book per subject. For example, for the 5 English books, you can just simply make it one group, right? So that should be 5 English books. So let's say it's 1, 2, 3, 4, and 5, right? 1, 2, 3, 4, and 5, right? There we go. So that's our 5 English books. Now we have 7 science books. So that should be, I guess, more books. That's 1, 2, 1, 2, 3, 4, 5, 6, and 7, right? 1, 2, 3, 4, 5, 6, 7. That's our 7 science books. We have 4 math books, just fewer. 1, 2, 3, and 4. And we have 4 for social studies. All right. So first, all right, we group them together, okay? We have to put them next to each other because the problem did specify that they have to be arranged next to each other. Okay, so if we're going to put them in groups and arrange them in this particular group, all right, thus we only have 1, 2, 3, 4 groups, right? We have the group of English books, we have the group for science, we have the group of math books, and we have the group of social studies books. Thus, the problem simplifies to just arranging 4 groups, right? So how many ways can I arrange 4 groups in a line? Okay, so since I need to arrange all 4 of them, that is P 4 taken 4, all right? Because I need to arrange all of them, right? I need to choose all 4 from the 4 different groups. So P 4 taken 4 is simply 4 factorial, okay? So this one, arrange books per subject. All right? Now, 4 factorial is actually a very small number. Because 4 factorial is what? It's 4 times 3 times 2 times 1, which is 24. So you might wonder, Mr. Tricino, definitely it's not just 24 ways to arrange those, right? Because definitely it's easy enough for me to figure out, more than that. That is correct, all right? So what are we missing here? The thing we're missing here is that for each group, right? For example, for English, for each group, let's say this is English book 1, English book 2, English book 3, English book 4, English book 5, right? Within each group, those books actually can be arranged within themselves, right? So in the group of the English books, if I have 5 books that I need to arrange all right, so this is just simply P5 taken 5. Thus, for English, among the English books, that's already 5 factorial ways of arranging them. If you repeat the same logic for science, math, and social studies, you should be able to figure out that the number of ways that you're going to arrange science books is 7 factorial. And then for math and social studies books, both of them are 4 factorial each. All right? So therefore, because not only do you need to arrange them per subject, each subject also has a small arrangement within themselves. Thus, this 4 factorial has also need to be multiplied by the number of ways that each group of books can be arranged within their group subject. So that is 4 factorial times 5 factorial for the science times 7 factorial for the 5 factorial for the English, 7 factorial for the science, and then 4 factorials for math and social studies. And definitely this should be the correct answer. Now that's actually a very big number now that you're actually looking at it. All right. This is definitely beyond a manual counting skill, right? But definitely this checks out, right? If you try to if you try to use the same logic for fewer books, okay, let's say you're only arranging, let's say 8 books, 2 per subject, right? So that's what? That's 4 factorial, then times 2 factorial, times 2 factorial, 2 factorial, 2 factorial, 2 factorial. So that is actually a much fewer, right? I mean, it's still I'm sorry. Yeah, it's still a lot, but it's much fewer than what we have over here. All right. So this is how you count objects that need to be together. All right. So I hope that you understood this particular example. Remember, if you have more questions on how the count was done, definitely do post your questions in the weekly Google Docs so I can respond to them. All right. So let's go switch back to our. All right. Okay, so if you actually scroll there, all right, we actually got the same answer. So of course, I will be attaching this document, the one I'm discussing, onto the resources that I will be providing for next week, so you can actually read it. But hopefully, my explanation, all right, is clear enough. Plus, reading this should make you understand it better. But remember, if it's still unclear for you guys, definitely do post questions on the weekly Google Docs. All right. Okay, so now we go to our second example. All right. So in this second example, so we're going to arrange objects containing non-distinct objects. So how many ways can you arrange the letters of the word Mississippi? All right. Okay. So take note, this particular example, we are talking about objects which have non-distinct objects. That means there are similar objects within themselves, right? So if you would like to try it on your own, of course, you may pause the video, try to work it out, and then later unpause it to view the solution. All right. I think that should be enough time for you guys to have paused the video, try to work it out on your own, and then unpause it so that we can go over the solution. All right. So the next slide here actually outlines the solution, but I think it's easier if I actually go over the solution with you as if I'm answering it the first time. So we're going back to our whiteboard. All right, there is our magical word, right? The state of Mississippi. I wanted Maryland, but it has few common letters. I think only the A's are repeated, so it's not too much of a challenge as an example. All right, so Mississippi. So this one has how many letters? Remember, we're going to rearrange all the letters here, right? So definitely we need to use all letters. So first we count how many letters. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11, all right? And since we need to choose all of them, you might think, Mr. Tricino, this is just simply 11 factorial, right? Because you have 11 letters that you need to arrange, right? So it's just P, remember, because of the word arrange, thus you need to use permutations instead of combinations. So you might say this is just P11 taken 11, which is simply 11 factorial. However, the problem is the same letters. For example, consider this 2S right here, okay? So if I interchange their position, would you have noticed? I mean, you would have if we actually put subscripts, right? This is S1, that's S2, S3, S4. So if I interchange S1 and S2, yes, I would have noticed that. But what if there are no subscripts? There's just plain 4 S's there. And I interchange any two of them. Would you have noticed that? No, right? The same goes with the I's, right? So therefore, 11 factorial is definitely an overcount. Because this 11 factorial considers the fact that those letters which are the same are being arranged with each others. So this 11 factorial includes switching those two S, right? Or switching this first S with the last S, right? That is part of the 11 factorial. Okay, so 11 factorial is it's a very, very big count. All right. So maybe there is, maybe there is a way to remove this parts which required, which we counted by mistake, because we just assume that we're arranging 11 letters. We just went straight for 11 factorial. All right. Okay. So first we identify similar letters. So if you look here, only M is actually the single letter here. We actually have 4 I's. All right. That's 4 I's. We also have 4 S, and we have 2 P's over here. All right. So identifying what the common objects are. In this case, there are letters. So identifying what the common objects are, it makes it easier for us to identify the number of ways they arrange themselves. All right. So let's focus on the 4 I's. So the question is, how many ways can I arrange 4 i's? Oh, that's simple. That's P 4 taken 4. You have 4 i's. You want to arrange them. That's 4 factorial ways. All right? The same is true with S. Now for P, because you only have 2, you only need, it can only be arranged in 2 factorial ways, which is just 2 ways. All right? Just interchanging them. All right. Now, what do we do with these ones? All right. So 4 factorial is the number of ways you arrange the i's. 4 factorial, the number of ways you arrange S. 2 factorial is the number of ways you arrange P. All right. The total number of ways that you can arrange the letters of Mississippi is 11 factorial, but then you will have to remove the number of ways that you arrange those similar letters. So thus 11 factorial needs to be divided by 4 factorial. This effectively removes the number of ways that the i's can be arranged. All right. You also have to divide it again by 4 factorial, because this 4 factorial here removes the number of ways that you can arrange the S. And then finally, you divide it also by 2 factorial to remove the number of ways that you can arrange the P's. All right. Thus, the total number of arrangements that you can have for Mississippi is simply 11 factorial divided by 4 factorial, 4 factorial, and 2 factorial. Of course, these factorials at the bottom are going to be multiplied with each other. But if, as I mentioned, if you're going to use a non-scientific calculator, something that could not actually display something like this, you need to calculate it as 11 factorial, then divide by 4 factorial, divide by 4 factorial, divide by 2 factorial. So this is how you would do it in a regular scientific calculator. Something that cannot do, right? A fraction notation. Right? Another way is, if you are fond of using parentheses, you can also compute this by doing 11 factorial divide by, then put a parenthesis. 4 factorial times 4 factorial times 2 factorial. Right? So any of these 3 methods, 1, 2, and 3, should give you the correct count. Right? So this is how you approach arrangements which have similar objects, right? Because you need to remove those arrangements of similar objects within each other, right? Because if you just arrange them without regard to the internal arrangement of the similar objects, then you are definitely over counting. You're counting more than what is the actual count. All right. Okay, so let's go back. Okay, so as we go over to the next slides, all right, we actually see some discussions here, and definitely the answer is 11 factorial divided by 4 factorial times 4 factorial times 2 factorial, right? So this is the number of ways that you can arrange the letters in the word Mississippi. You can actually try and Google that, and you will actually get the same result. All right, so this is the idea of how you arrange objects which have similar objects within them. All right, now we are down to our very last example. All right, so the very last example might be familiar to some of you, those who play card games. Now, counting, of course, I think one of the more useful things that they use counting is definitely gambling, right? Lottery tickets, card games, and so on and so forth, right? So the third example actually makes use of the game poker. All right. Okay. So for those who are not aware, right, I'm going to try and see whether I could actually find more information on how poker is played so that we can actually count the number of possible ways that you get a particular combination. So original poker is a 5-card game, all right? So usually the game is played wherein a player is handed 5 different cards. Now, a particular combination of cards is classified to be higher than other combinations, right? The rarity, all right, or the fewer the number of ways that a particular combination can be formed definitely outlines the value of the card combination. All right. So for those who do not play cards, let me introduce how a deck of cards work. So a deck of cards is usually made up of 52 cards. Okay. All right. And then these 52 cards are divided into what we call 4 suits. So the suits, okay, are diamonds, hearts, spades, and clubs. All right. I will show you a picture. All right. So here we go. All right. So these are actually 4 of the cards out of 52. These are the ace cards. All right. So the A over there symbolizes the ace. Right. So these are called aces. All right. So the suits are actually the symbols under those letters. So usually for cards, there would be a particular character on top. It's either a letter or a number. So for the numbers, they don't have a 1. The numbers begin with a 2 all the way to a 10. And then for letters, you have a J, a K, a Q, a K, and an A. All right. So these are the 4 aces. The suits are actually the symbols under the characters. All right. So this one is referred to as a diamond. This one is referred to as a heart. That is referred to as a spade. And this one is referred to as a club. Right? Okay, so notice the diamonds and the hearts are red colored cards. This is, of course, usual. The spade and the clubs are black colored cards. All right. So this is how you actually see the suits. Right? Now, as I mentioned, we're going to switch again to the main example. All right, to talk more about the deck of cards. Right? It's important to talk about the deck of cards, as some of you might not be aware of what is inside a deck of 52 cards. So it's 4 suits in 2 different colors. Right? The suits are diamonds and hearts, spades and clubs. Each suit, right? So the diamond, the hearts, the spades, and the clubs, they are made up of 13 cards, numbered from 2 to 10, and it has letters, characters, which are J, Q, K, and A. So the way they are remembered is that J stands for a jack, Q stands for a queen, K stands for a king, and A stands for an ace. All right. So usually the values, they go this way. So the lowest value is sometimes 2. All right. Then it increases as it goes to 10. Then after 10, you have a jack, a queen, a king, and an ace. Now in poker, also in blackjack, if you would like to know, A actually is a special card. All right. As it can either be played as the lowest or the highest card. So it can be played as the highest card, so it's higher than the king, or it can be played as the lowest card. which means it comes before a 2. All right? So this is the duality of an ace. All right. So now that we understand what a deck of cards look like, all right, what the characters there mean in relation to poker, we now go with particular examples. All right. So now, okay, so assuming, all right, that you are going to draw 5 cards, you're playing for yourself, right? And you're thinking, okay, how many ways can I draw a particular combination? All right, so the first question is, determine the number of ways one can draw a 5-card hand, right? So you're trying to draw 5 cards, and that 5-card hand would actually be a flush. So a flush is a group of 5 cards which belong to the same suit, right? So they can all be hearts, they can all be diamonds, they can all be spade, they can all be clubs. All right. The second question, oh wait, let me of course show you a particular example for a flush, so that okay, so here we go. All right, so this one is an example of a flush. All right, so these are all cards, these are 5 cards all belonging to the suit of hearts. All right, so you have a 2 of hearts, 3 of hearts, 7 of hearts, 8 of hearts, 10 of hearts. So it does not matter which 5 cards belonging to hearts you actually get, as long as they all belong to the suit of hearts. All right, so this one is an example of a flush. All right. Okay, so let's go back to the next question. Let's see what the next question is. Okay, so for the next question, okay, what about of getting a straight? So a straight is 5 consecutive cards of increasing value. Now remember, pay attention to the special value of an ace. An ace could be the lowest card, right? Which means it could come before the 2, or it could be the highest card, which means it comes after a king. All right? So in number 2, it says you need to figure out how many ways can you actually draw a straight, but not a straight flush, right? So what does that mean, right? Because I'm pretty sure not a lot of you might know, or not all of you at least, would know, right, what a straight and a straight flush is. So a straight is a combination of 5 cards, right, that is arranged in terms of increasing value. Now note that the suits are not very important for a straight. Here you go. Right? So this one is an example of a straight. Notice you have an ace in its lowest value form. Then you have a 2, a 3, a 4, and a 5. So these 5 cards are arranged in increasing order of value. So this one is classified as a straight. Right? It's simply a straight because the 5 cards do not belong to the same suit. So the A belongs to clubs, the 2 belongs to spades, the 3 for diamonds, the 4 and 5 to the hearts. Okay, so this one is simply a straight. Now, a straight flush, on the other hand, has the same properties as a straight. However, it should also be a flush. Right? So an example of such is as follows. All right, so here we go. So here we have 3, 4, 5, 6, 7. So 5 cards, right? 5 cards definitely of increasing value. So definitely a straight. And notice they all belong to the suit of spades, which means not only is this a straight, this is also a flush. Thus, it is called a straight flush. All right, now this one is definitely very rare. Okay, so the question is for number 2. All right, how many ways, all right, can you actually determine, or how many ways can you actually draw 5 cards, which would result in a straight, okay, but not as a straight flush. All right. Okay, so if you would like, let's start with number 1 first. Okay, so I'm going to pause. I'm going to allow you to work on these 2 examples separately. We're not going to discuss them all at the same time. So we're going to start off with number 1. So I'm going to allow you to pause the video right now so that if you'd like to actually work on it, okay, yeah, you may do so. Then after you work on it and then you'd like to see the answer or the solution, you may unpause the video and I will discuss that. All right. I think that's enough time for you to have paused the video, made a decent attempt for number 1, and then unpause it for us to discuss. Okay, so definitely the slides that come after this one discusses how to determine a flush. Okay, but I think it's much easier if I actually go over with you guys in real time-ish how to compute for the number of ways a flush is obtained. All right, so let's go to my whiteboard. Aha, here we go. My whiteboard. Okay, so we're looking for a flush. Okay, which means it's 5 cards belonging to the same suit. All right, so there might be several ways of approaching this problem, but for me, right, I would focus more on the important characteristic of a straight flush, right? Which is it has to be from the same suit. All right. Okay. So the first thing I need to do is determine what suit am I going to get. Okay. Right. So, so what suit am I going to look into? All right. So how many suits are there? There are 4 different suits: diamonds, hearts, spades, and clubs. All right. And out of those 4, I only need to get 1. All right. Okay, since it's only 1, it does not matter whether we use permutations or combinations because both of them lead to the same answer, right? Okay, so you can do this as P 4 taken 1 or C 4 taken 1, right? Both definitely give the same answer. Both actually leads to 4. Right? You can, of course, check that computation by computing each one on your own, right? But regardless, definitely they both equal to 4. Right? Me personally, I have a bias on combinations. I would use that notation instead because it does not need to be arranged, right? I mean, I'm only choosing 1, so I'm not going to arrange it. So I'd rather, think of it as more of a combination. But regardless, because you're only choosing 1, you may use either a permutation count or a combination approach. Both answers are the same. All right. Next. So after we've chosen which suit we're going to get it from, okay. So is it going to come from the diamonds, the hearts, the spades, or the clubs? Let's say the hearts because that was my example, right? Okay. I choose hearts. Okay. So now that I've chosen what suit is going to come out of, I need to choose now 5 cards from the same suit. Okay, all right. So how many cards are there per suit? All right, so let's review. Okay, so there are 52 cards. There are 4 suits. So each suit should have 13 cards each. Aha. All right. 13 cards each. Okay. All right. So I need to choose 5 cards out of those 13 cards in that particular suit. So if I choose hearts, that means I have to choose 5 heart cards out of the 13 heart cards. Makes sense, right? And to be able to do that, now take note, you are only choosing them. It does not need to be arranged, right? The rule for flush is that as long as you get those 5 cards, all coming from the same suit, that is definitely a flush, right? So since there is no arrangement necessary, we're going to count this through combinations. So thus, let's use red, of course. So that would be C, 13 taken 5, okay? Because out of the 13 heart cards, I will be choosing 5 of them, all right? So therefore, okay, how many ways can we actually draw a flush? It has to be the combination of these two. You need to choose the suit first, then you need to choose 5 cards from that suit. So thus, the total number of ways that you can get a flush should be the product of these two events. So that would be C, 4, choose 1, which is 4, times C, 13, choose 5. All right, so let's just see, it's 4, C, 13, choose 5. Right, so if you'd like an actual number, you may actually calculate C, 13 taken 5. Right, that would be the number of ways you can actually draw a flush. All right, okay. So those number of ways contribute to its rarity, right? So if you would actually like to read more, I will try to look for some text on poker rules so that you actually understand which 5 card combination is the rarest, and you can actually count why it's the rarest, right? Okay, and then why some cards are actually of small value. All right, so this is definitely the way. All right, this is definitely a number of ways that a flush can happen. All right, so let's look at, let's go back to our example, see whether, see whether, aha, there we go. All right, C of 4 taken 1 times C of 13 taken 5. All right, so if you multiply those, voila, you have your flush combination. All right, so now we're ready for number 2. All right, so let's go back to number 2. So remember, for number 2, we are looking for the number of ways that it has to be a straight, which is 5 consecutive cards of increasing value, but not a straight flush. All right? Okay, so if you would like to try this on your own, you may pause the video right now and then unpause it later to check your answers. All right. I think that's enough time for you guys to have paused the video, make a decent attempt on the answer, and then uh, unpause the video to actually see the solution. All right. So although the next slide will actually outline the solution in text, I think it's best if we actually go over this in real time-ish. All right, so back to my whiteboard. So we are looking for a straight, but not all right. Let's underline that, but not. All right. So, okay. So first, we need to figure out what are the possible combinations for getting a straight. Right? Okay. All right. So the smallest straight that we can have should begin with an A, and then it should end with a 5. All right. That is the lowest possible straight we can come up with, right? Because the lowest value is an A, and the highest value is a 5. All right. The next higher straight would, of course, start from a 2, and then it should end at a 6. All right. Okay. All right. So the next one would be from 3 all the way to a 7. And then if you continue this, eventually the highest possible straight that you can have would start from a 10 and end with an ace, right? That's if you like to count, that would be 10, jack, a queen, a king, and an ace. All right, 5 cards. That is the highest possible straight. All right, okay. So these are the possible combinations of getting a straight. Now, this is important because it definitely makes our analysis easier. All right. So the thing about straights, all right, is there are limited combinations of them. All right. So I think the easiest way to be able to count the number of combinations is to focus on a particular card. Me, I would like to focus on where they begin. Right? So why is it important to focus on where they begin? Because if you know where they begin, then you understand what the order of the cards is, or how many choices for the next card there will be. Okay, all right. Okay, so to illustrate, let's have 5 cards here. 1, 2, 3, 4, 5. So for the first position, right, we actually have from A all the way to 10. That is actually 10 possible choices, right? Okay, that's 10 possible choices for the first card. That's fine. However, once we go to the next card, there's actually only one choice left, right? Why? Let's say you begin with a 2, all right? Okay, so the first card is a 2. Now, for it to be a straight, the next card can only be a 3, right? I mean, you might argue that Mr. Josino, you're focusing on the arrangement, so we're going to like use permutations here, but later we will clarify that, right? So the next card, for it to be a straight, should be a 3. Then after that, the next card should be a 4, the next card should be a 5, and the last card should be a 6. All right? So therefore, this one is simply equal to 10. All right? So this is the fundamental principle of counting weight. All right? However, all right? However, this one, right, we can actually rewrite it, right, as just C 10 taken 1. So this C 10 taken 1 refers to the number of ways you can choose one card from the 10 possible starting positions. Right? Now, why am I using C instead of P? Right? Because as a straight, doesn't it have arrangement? Well, actually, you might say that you can also say it's a P of 10 taken 1. This will give you the same answer, 10. Right? But why am I using C? Now, remember, it does not matter in what order you pick these cards. As long as you have those 5 cards with you, you can arrange them even in your mind, and they would be considered straight. So it does not matter whether you draw the 2 first, then afterwards you draw the 6, then the 4, the 3, then the 5. It doesn't matter if you draw them out of order. What's important is you have a 2, a 3, a 4, a 5, and a 6 for that particular hand to be considered a straight. All right? So in terms of getting a straight combination, there are only 10 possible combinations for getting a straight. One that starts with an ace, another that starts with a 2, eventually one that starts with a 10. Those are the only possible combinations. All right. Okay. So that makes sense. All right. All right. Okay. But remember, as a straight, all right, suit is not an important consideration. Okay. So therefore, you actually need to pay attention to the suit per card. All right. So what suit should each card be? Right? Okay. So the first part, it allows you to figure out what straight you're going to have. The next part, we're going to see what suit is each card going to be. All right? Okay. So for the first card, okay, we can choose any one of the 4 possible suits. So therefore, we have 4 choices here. Okay. For the next card, we can again choose any of the 4 possible. Remember, a straight does not pay attention to the suit. As long as you get those card values, that would be considered a straight. All right. So therefore, the next card, you still have a 4. And you might say, oh, all right, I guess it's all 4 for all 5 of them. Aha. All right. So you might say, oh, thus, in terms of suits, that is simply 4 to the 5th. Right? However, this one is an overcount. It's not 4 to the 5th. Right? Right? It's not 4 to the 5th. Why? Why can't it be 4 to the 5th? All right. Okay. Because note that we cannot have a straight flush. Right? So how are we going to get rid of that part for it to end up not as a straight flush? All right. So let's say, because you're allowed to choose any of the 4 suits in the first card, let's say it comes out as a heart. Right? For the next card, you are allowed to choose any of the 4 suits again. So let's say it comes out as a heart again. Right? Same with the third card. Same with the fourth. All right. Now for the third one, for the fifth one, right? You cannot have 4 choices. Because if you have 4 choices, then you are actually accepting the possibility that it comes out as a heart again. Thus, the last card is not possible to be 4. You're only allowing it to be 3 choices. All right? Just to make sure that the last card would be a different suit if the first 4 actually turns out to be from the same suit. All right? Okay? So this 3 here is a guarantee that it would turn as a different suit as opposed to this first 4, which has a possibility of turning out to be from the same suit because you're choosing one suit out of the 4 possible suits. So if the first 4 turns out to be all from the same suit, then you have to restrict the last card to make sure that it does not come from the same suit. Otherwise, there's a probability, there's a chance that it actually turns out as a straight flush. Not saying that it's a bad thing, it's actually a good thing because a straight flush is definitely rarer than a straight. All right, so here you have 3. So therefore, what you have here is simply 4 to the 4th times 3. Right? Sometimes I just refer to it as C4 choose 1, right? Raised to the 4th, right? Because of these 4 things. And then times C3 taken 1. All right? Therefore, the actual number of straights that can be made, excluding straight flushes, would be the combination of these 2 properties. So it should be C of 10 taken 1 times C4 taken 1. Oops, I forgot the 1. Raised to the 4th because the 4th cards has to be from 4 different suits. Right? Or the 4 cards has to be one of the 4 different suits, except for the last one, which has to be guaranteed to be different from at least one of the first 4. All right? So let's say the first one comes out as a spade. So the last card is everything else except a spade. That guarantees it will not be a straight flush. All right. So if you actually multiply this, right? So I think it's not too difficult. I mean, 4 to the 4th is 256 times 10. That's 2,560 times 3. That would be what? That would be 7,680. So there are 7,680 possible ways of getting a straight, but not a straight flush. All right? You can actually research that. See if see if I actually counted it correctly. But I'm pretty sure I did. All right. So this is how you actually count the number of ways that it comes out as a straight, but not as a straight flush. Okay, so I hope, right? Oh, wait, let's go over, of course, to the main lecture. See whether we actually, all right, have the same answer. All right, here we go. All right. Okay, so the total number of ways to pick a straight without selecting a straight flush is definitely the same one we got from the whiteboard. All right, so I hope that this one is quite clear. I'll definitely put up some questions, right? Some poker questions on combinations, on how many ways you can get get a particular hand or something. So definitely that is easy enough to research. All right. I'm not saying that you actually play poker, but you understand its rules because counting it is one of the things that mathematicians actually pay attention to, right? Because definitely in gambling, There's a lot of money involved, and those who actually understand math, right, in its most applied form, actually tend to do better, right? So, okay, I'm not saying this, of course, to promote poker. No, don't gamble. Play poker out of leisure and pleasure, right? Don't do it for don't be a professional poker player. That I'm saying, if it's your dream, maybe, but definitely gambling is not recommended by me. Okay. Now that we have made that clear, made my position on gambling clear, I hope you guys learned something from this week's lecture. So next week, we're actually going to begin probability. All right. So this will be the last time we're actually going to be doing counting. However, when we do probability, it still involves counting, as later you will realize how I define probability. Right. So I hope you guys keep staying safe, and I hope that if you actually have more questions, you do post them in the Google Docs. So I guess stay safe, right, and always be well. Bye.